back to the seminar series. Today we have Kaustubh speaking for us. As you see, he's going to be speaking about exoplanet science. He will talk about our instrument that is currently being built. Hopefully will be soon commissioned. Kaustubh, he did master studies at KU Leuven, and then he moved for his PhD to the Netherlands, to Amsterdam, and then took a long-term postdoc in Switzerland. And after that, he decided to move back to KU Leuven. Maybe he loved KU Leuven so much that he wanted to be back. And he is currently on the position of research expert, and I believe it's 50-50 between Royal Observatory in Brussels and KU Leuven here. All right, so the floor is yours, Kaustubh.
Thanks, Andrew, and thanks everyone for coming. Today I'll talk about this new topic for me, exoplanet science in the era of MARVEL. So this is not going to be an instrumentation talk. So I'll talk from the perspective of exoplanet science mostly. But it's also what I would like to highlight is MARVEL is coming up in at a time where exoplanet science is really peaking, or even maybe even doing so good that MARVEL can not only benefit from it, but MARVEL's role will be very crucial also for a lot of work which is going on in the global exoplanet community. So this you might have seen many times by now. This is something which I saw first in the lecture of Alex de Cotter, surprisingly. But this is a very nice summary of how different exoplanetary systems are in terms of orbital radius, because you see solar system in the middle, and the dotted dashed lines are the orbits of solar system planets. And all the other planets you're seeing are the exoplanets being detected mostly by Kepler. So this is like more than 10 years old now. But the colors also show you how different their equilibrium temperatures are. So they could be very hot and also very cold. So over time, when people did population studies from observations of these Kepler planets, they understood that there is like a very peculiar exoplanet distribution, or the occurrence diagram we see. And on the vertical axis, you see number of planets per star versus planet size. So Earth is at 1. And you see most of the planets were detected at the time were much larger than Earth, at least 10-20% larger than Earth. And now we know planets smaller than Earth as well, but there are much fewer than what we know for larger ones. And that is due to observational bias. So what you see, there are certain features in this diagram. So one is like a valley between two planet populations. This is called the radius valley, and then there is a cliff called the radius cliff as the planet population decreases above the size of almost half of Neptune. So in principle, just looking at this diagram, one can divide these planets into 3 classes. Rocky, maybe like Earth, sub-Neptunes, not sure where exactly they fall in, but between gas giants and rocky. And then, of course, gas giants are probably more like Jupiter in terms of composition. And in this talk, whatever I will call small exoplanets are the 2 small classes, rocky and sub-Neptunes. So as I already said, there's a bimodal distribution in the small exoplanet population. What is really interesting feature is only about 1% of exoplanets are gas giants. So this is also important because in our solar system, we have 2 gas giants and 2 ice giants. In principle, you can call these 4 very gassy planets and 4 rocky planets. So in reality, when we look at mostly Kepler data field, we see only 1% of exoplanets are gas giants. Another thing to remember is when gas giants are there, they dominate the planetary mass. So they have taken away, eaten up all the planetary mass there is in the solar system. So one can ask, what really shapes this exoplanet distribution? Why there are these small exoplanet populations and gas giant populations? If you try to introduce the orbital period also of the planet, so on the vertical axis you have the radius, and the horizontal axis you have the intensity, stellar intensity relative to Earth, but effectively this can be translated into orbital period. So when you do that, you again see two populations. The top one are sub-Neptunes and the bottom one are rocky. Another way to visualize this is, like I said, with the orbital period. And this becomes a little bit more clear here, that these two populations have a distinct characteristic. And this has been discussed in terms of the photo-evaporation of sub-Neptunes leading to the formation of some of the rocky planets. So this photo-evaporation desert, what you see on the top left of the left figure, is also an interesting characteristic, that there is no planet more or less in this desert. But if you go to larger radii, there are some planets discovered now. So what does this sub-Neptune desert tell us? Is it a signature of evolutionary mass laws? Can it tell us something about the planet formation location for these planets? So there are questions like these, they arise from these observations. So now we just talked about radius, but when you introduce mass, one can calculate the density of these planets. And this is precisely what is shown here. These are the RV measurements could be used to determine planetary mass. I will come to that later. But what you see, all these gray dots here are observations, and these solid lines are isocomposition lines for spheres of hydrogen, water, rock, and iron. And you can see that the bottommost population clings around the green line, which is rocky composition. As you go towards the top, extreme top, these planets cling to the hydrogen line. And the planets in between fall, the sub-Neptunes fall all the way between very close to rocky to in between the hydrogen and water lines. So this gives you a first order impression of what kind of compositions these planets can have. So when you try to imagine what really this means, I like to think of it as the rocky part being made by refractory elements like iron, silicon, magnesium, calcium. Of course, these are in the form of oxide silicates, so these are not in elemental forms. But this is what makes up the rocky part of these planets. But then there is also the gassy part, the hydrogen-rich atmosphere, hydrogen-helium-rich atmosphere. And this really is shown in proportions here. Gas giants really comprise mostly of gas. Rocky planets comprise mostly of rocks, but sub-Neptunes are kind of in between. Some more new information on small exoplanets has revealed that this is although only for the planets around M-dwarf stars, that the radius mass relations of these planets suggest two populations. So these are not fits, but these are simply, again, isocomposition lines for 50% water plus 50% Earth-like planet and Earth-like planet. And what does this probably tell us is their sub-Neptunes probably, or small exoplanet populations may not just come in these two varieties. There could be some additional varieties as well, like composition with rich in water. There could be many other possibilities because to a certain extent, mass radius relations are degenerate. So you can produce same bulk densities for different compositions. Another aspect is, can we tell by looking at these observations which planet formation pathway was favored? So on the left, you see planet migration model. This is the classic embryo migration model, where planetary embryos grow in the presence of the nebular gas when hydrogen is present, and they become ice-rich. And once they migrate, they tend to retain their gas-rich or ice-rich composition. There is also a pebble drift model, which allows for what is called as inside-out planet formation. So these they allow the growth of rocky planets favorably due to pebbles, and this results in more rocky population than icy population. So can the observations of small exoplanet populations allow us to determine which planet formation pathway is more common than the other? So there are a lot of fundamental questions to be answered through these observations, which I have summarized here. But what is pretty evident, at least to me, is these cannot be answered without precise determination of exoplanet masses. And this is a very important point for me. So a little bit of an overview of exoplanet detection methods. One would think that just like you photograph a star, you would photograph a planet, and you can find the planet. But it turns out it's extremely difficult, and a lot of people here in the audience know this much better than I do. So only few direct imaging planets have been detected, and this is because the brightness contrast can be really high. In the visible, they can be really large. In the infrared, they are a little bit lower, but it's still a challenge to block the stellar light, the parent star's light, in order to see the planets. By the way, I didn't really say that this HRH 799 system has 4 planets. So you can see the 4 planets, like one here, one here, one here, and I think one of them is here. There is another technique called transit photometry. So the Kepler Space Telescope and before that Corot, they led the way to do space-based transit photometry. And this really allows you to determine also the planet radius. I'll explain that in a bit. There's also Doppler spectroscopy, which allows you to detect in the shift of spectral lines as the gravitational pull of the planet changes these lines coming from the star. So this was actually the method with which Didier Queloz and Michel Mayor detected the first exoplanet, which also completes 30 years, as we learned in Peter's talk a couple of weeks ago. And this, for this discovery, they were awarded a Nobel Prize in 2019. There are other detection methods. They are less popular, or rather they result in fewer planets, not mentioned here. There's also a characterization method, which again is about transits, but it's about spectroscopy. So a little bit more detail about this. So what do you really learn from transit photometry? So you can determine the radius of an exoplanet. How is this done? You would get a photometry light curve like this. So what you see here is the normalized light, and as the planet passes in front of the star, there's a dip. And this dip is due to the starlight blocked by the planet. So this is actually proportional to the area blocked by the planet. That's why this transit depth is proportional to the square of the planet's radius over star's radius. And this figure, I forgot to add the reference, but this is actually from the Nobel Prize winning paper. Another way transit can be utilized better is to do spectroscopy with it. And this is what James Webb is doing now, and ARIEL, a space mission, will be doing in the future. The starlight can be split into different wavelengths. And when it passes through planet's atmosphere, these different wavelengths carry different signatures. So for example, in the optical, some of these signatures are the cloud signatures. Then there is also signature of sodium, and as you go to infrared, there are signatures of H2O, carbon-bearing molecules, and all of this. So this is an interesting avenue to understand in detail the chemical composition of the atmosphere. Interestingly, Venus's atmosphere was first discovered by its transit in 1761. And this is a photo of a recent transit of Venus in 2012. I unfortunately missed it. I think whoever saw it was very lucky. Then the third technique is radial velocity method, or Doppler spectroscopy. What this really gives you is the minimum mass of the exoplanet. But for the transiting exoplanet, this gives you close to its true mass, because the inclination angle, the sine I, is almost 1. So this K is the semi-amplitude, and what you can again see here, there is also some dependency with stellar parameters. So in general, the knowledge of the star is also very important to determine the planetary mass. So there are quite a few RV facilities. I have just shown 3 here. One of the most popular ones has been HARPS, and it really went down to precision of 1 meter per second. This allowed the determination of masses of really small exoplanets, and this has been very fruitful for the community over the years. And then recently came Espresso, which with a very ambitious aim of 0.1 meter per second on VLT, which allowed even great science that one can do. There are other spectrographs like Carmenes, which also do the competitive RV precision of 1 meter per second. All these facilities really allow for the determination of exoplanet masses. So on the left is a figure from Gerst's paper. So what you see is the concept of MARVEL. And so MARVEL is basically located very close to Mercator, those who have been there. So it's on the back towards INT. And on the right, you see it's actually one of the latest images. So it's very fascinating to see this concept being turned into reality. There is a quite huge instrumentation effort going on. I don't know much about this, or I don't understand much about this, but it's fascinating to see how this instrument has turned into reality. And as I'm new to consortium, I thought this could be a good opportunity for me to learn about MARVEL. So I'm going to ask you to help me with this. So there's a little quiz we are going to play. So I hope your smartphones are working. So what you need to do is go to this website, kahoot.it. It can be done through browser, and enter this game pin. I'll give another minute and then I'll start. Sorry? Oh, sorry guys. I'm using the free version. I didn't know it was only 11. I thought it was 20. But okay. Okay, sorry whoever could not join. So it's also fastest fingers first. So the sooner you press the answer, higher points you get. So what does MARVEL really stand for? So you have to match the color on your smartphone with the options you see here. Okay, thank you for this answer because I didn't know this. Okay, so we have some fastest fingers first. What are the two resolution modes of MARVEL? Thanks for that as well. I never remember this. Oh. What is the spectral coverage of MARVEL? Okay, fantastic. Thank you. I think we are doing very well here. So congrats to everyone. Okay, so at least now we can answer these 3 questions in the future. Okay, so this also summarizes some of the answers. So MARVEL really is an array of 4 telescopes. And these 4 telescopes are connected to one spectrograph. And I think this wavelength calibration is also a very key part of MARVEL as far as I understand. And this single spectrograph records 4 science and 1 calibration spectrum per exposure. So this really allows the flexibility for MARVEL to point at 4 different objects simultaneously or 1 object for higher precision. And the high precision really, the ambition of MARVEL is to really go down to 1 meter per second. So this really opens up a huge parameter space for small exoplanets. Yeah, there are some more specifications apart from some of the answers we learned. Yeah, I think this is more or less the repetition of that. So one of the important things for MARVEL is which stars it can really observe. So for example, this figure shows you if there is a 5-minute exposure, you would be on this black solid line. So you could do really not so faint stars. But if you increase the exposure time to about an hour, you really can go even beyond 11 V magnitude stars. So this really is fantastic because a lot of the TESS simulated host population lies here. And there's plenty of opportunity also for even fainter stars, so which is also nice. But of course, they come with their own problems of stellar activity. So why there is need for MARVEL to achieve this ambitious 1 meter per second RV goal? So on the left, you see the RV semi-amplitude plotted as a function of orbital period of exoplanets. And all of these exoplanets plotted here have no real RV measurements until now. In fact, if you look at the exoplanet database, only 900 exoplanets have RV measurements, and 3,500 exoplanets do not have RV measurements. Out of that, if you apply the V magnitude 11 criteria, about 320 transiting sub-Neptunes fall between an RV of 5 meter per second and 1 meter second. So if MARVEL really goes from 5 to 1 meter per second, this will open up all these small exoplanets, more than 300 even. And this doesn't include any PLATO data, obviously, but also the extended TESS mission. So both these missions will even populate this space more. On the right, you see synthetic exoplanets, and all these synthetic exoplanets are generated from population synthesis models. This also gives you an idea of how many more planets could there be between an RV of 5 and 1 meter per second. So I'm thinking of MARVEL. What MARVEL can really do is MARVEL can become a global RV follow-up facility. So it really can go beyond just space missions. There are plenty of planets already there, which needs to have a follow-up. So mass determination of long-period exoplanets, especially for small transiting exoplanets, is going to be key. And this already, as I showed, without the extended TESS and PLATO missions, there are plenty of planets to be done in this regime. Then, of course, what MARVEL will do is provide follow-up for TESS and PLATO candidates. It will also help prioritize the list for ARIEL space mission, because ARIEL also has its own running target list. And MARVEL can also help ARIEL from the perspective of exoplanet host stars. So long-term monitoring of exoplanet host stars is something MARVEL can do very well. And then this will allow missions like ARIEL to have a better understanding of which planets to go for. Of course, stellar properties, as I briefly mentioned, are also important. So this needs to go hand in hand, the determination of masses and of exoplanets and understanding of stellar properties. There is plenty of additional science to be done with MARVEL. There is opportunity for discovery of non-transiting exoplanets from in transiting systems. There have been quite a few examples of these already. The monitoring of young star for direct imaging, understanding also their activity, variability in young stellar objects, astroseismology of massive stars. So there are many of these science cases, and a lot of these have been compiled in the MARVEL science case document, which the consortium also comes together to discuss and review. So there's a very ambitious goal which MARVEL wants to set, is to generate up to 20,000 RV measurements per year at 1 meter per second precision. Even I think 1/4 of that or 1/5 of that will be amazing science. So there are plenty of people involved in MARVEL consortium. So you can list, you can see the list with all the names. KU Leuven is obviously very heavy. Then there are partners from Australia, UK, Germany, Austria, Spain, Sweden, Denmark, and other places. So in general, there is a very KU Leuven heavy involvement in MARVEL. So a little bit of the context of why MARVEL fits right in the global context of exoplanet missions. So the TESS and CHEOPS missions have been currently extended. So they would be running until almost the end of the decade. Then James Webb is doing really great science. VLTI is also, VLT and VLTI are doing great science as well on exoplanets, direct imaging, RVN, and things like this. PLATO is going to do transit photometry of, with aim for habitable zone planets. Then ARIEL and ELT come towards the end of this decade. And MARVEL sits here very nicely with the ongoing missions and upcoming missions. So we can leverage very well the current science understood from ongoing missions and use it to direct the future missions, which is, I think, the best place for MARVEL to be in. Yeah, this is the main techniques, one of the key techniques these different telescopes use. There are also concept missions such as Habitable Worlds Observatory and LIFE, which really aim to target habitable zone Earth-sized planets around sun-like stars. So this is also, if funded, this will be the next big thing. So what do these different techniques provide us? So transit photometry provides us radius, radial velocimetry mass, transit spectroscopy, atmospheric composition. So mass and radius can be combined to determine bulk composition. And atmospheric and bulk composition can be combined to understand the composition of planetary layers. So basically the interior atmosphere characterization becomes possible for the first time for small exoplanets. So going back to the fundamental questions, I would like to highlight one of them, which I am working very closely since quite a few years, what is the composition of small exoplanets? But before we answer this question, we need to understand the interior atmosphere interactions of sub-Neptunes, which determine their observable composition and their true composition. This is because currently there is no model, no framework to do this. This is because sub-Neptunes are a class of planets which is unknown to solar system. They do not have solar system analog. So there is a lot of lab data missing. There's a lot of theory missing, which really requires quite a bit of community effort. To give you a little bit of context, so for example, if you talk about sub-Neptunes, there are plenty of structure and compositions being discussed. This is, on the left is the coldest sub-Neptune possible, on the right is the hottest. But even for the coldest, this is not a unique composition being discussed. There could be quite a few possibilities. So what really it means for us is try to understand the composition at the pressure temperature conditions relevant for these planets. So I will be choosing hot sub-Neptunes for the next few slides to go into a little bit more detail. This is also very interesting because this allows for the maximum interior atmosphere interaction, because magma being hot allows for a lot of intense chemical reactions between the atmosphere and the magma. And interestingly, unlike Earth's magma ocean lifetime was less than few million years, but sub-Neptunes can have a magma ocean lifetime of several billion years. This is because they have the right rock to envelope ratio, which does not allow the rock to dissipate the heat quickly enough, but because the envelope is also very optically thick, so it doesn't really allow the heat to escape even after a few billion years. So the approach I have taken is to combine astronomical and geochemical perspectives. So astronomical perspective says sub-Neptunes are just a downscaled version of gas giants. So what you see here, you just need to remember is, as you go to the right, the metallicity, the atmospheric metallicity of planets is increased. And you see change of composition from hydrogen-rich to hydrogen-poor composition, which makes sense. When you think of, from a geochemistry perspective, how rocky planets work, as you increase the surface pressure, your hydrogen content decreases as well. But also there is increase in compositions like CO2, CO, which is also the case on the left here. Recent works on different parts of this puzzle has demonstrated that the atmospheres of sub-Neptunes, because they fall in between those of rocky and gas giant planet atmosphere, they are more complex than what our current models can do. So that's why what we are doing with a bunch of collaborators is developing a new tool to model the atmospheres of small exoplanets. And this includes a lot of nitty-gritty details on different theories and extrapolations and inclusion of new lab data. Application of this, this tool shows us that there is a huge impact of interior atmosphere coupling. So on the left, you see the no magma case. So this is the astronomical perspective. So there is no interaction with the interior, no magma. This is what you will get. You will get a hydrogen-dominated atmosphere. As you increase the metallicity, the elements heavier than hydrogen will form gases in more dominant amounts, and that's why you see a slope going up. On the right, what you see is we switched on the magma-atmosphere interaction, and suddenly the picture becomes quite complicated. So some of the elements get alleviated, and others not so much. And on the left, I just demarcated two regions where this brown line is higher than this gray line. So this brown line is nothing but silicon-bearing gas. And silicon is mostly present, comes from the magma. Magma contains mostly silicon, and atmosphere generally is poor of silicon, hydrogen-rich atmosphere. So this regime is a magma vapor-dominated regime in the atmosphere. As you go to the right, it becomes helium or carbon-dominated. So where is all the hydrogen? So the hydrogen gets locked up in the magma because it reacts as well as physically dissolves in the magma as H2. And this makes a huge difference in its resulting composition in the atmosphere. So most of the hydrogen in the right figure is locked up in magma. And this creates a very complicated atmosphere. So what this means for some of the observables is what I try to show here is I try to calculate the bulk atmospheric metallicity. Sorry, the labels are missing here. So this red one is for silicon metallicity with Si over H. The orange is O over H. The blue and yellow are carbon and nitrogen over H. And this is helium over H. So what I try to present here, the metallicity is not uniform. It just changes. It's different for every element. Every element interacts differently with magma. And that's why you get, basically, if you were to calculate metallicity per element, it's very complex like this. And on the right side, you also have the C over O ratio, which is also one of the key observables, even with James Webb. So one of the future projects we'll be looking at is, can these signatures be observed in transit spectroscopy? This will require much more work than what we have done until now. Yeah, so just a reminder, I'm coming towards the end. So MARVEL sits very nicely between the current ongoing missions and upcoming future missions, and I'm really excited about that. So then I can summarize what I think is very interesting for MARVEL. There are quite a few fundamental questions which I think cannot be answered without long-term monitoring, and MARVEL can actually do that with not only for long-period exoplanets, small exoplanets, but also long-term monitoring of stars, exoplanet host stars, including activity and also determining the properties like effective temperature, metallicity, and so on. And of course, MARVEL creates a huge amount of synergies with current and future space telescopes. This really probably will help also MARVEL to stand out, again, contributing on longer period planets and long-term monitoring of host stars. So I will leave you with this video by Wim. He compiled, I think, all of this, which is very nice.
Thanks, Kaustubh. Well, people are staring at the process of building MARVEL. I have a question. Was Jake the one helping you to prepare questions for the quiz?
No, not really. It's a well-deserved win.
And there will be one question from me to everyone. What are the names of the 4 telescopes? It's time for questions. Who wants to be the first?
Thanks, Kaustubh. Ekdam mast talk hota.
Thank you.
My question is, actually, so you mentioned about the limiting magnitude in terms of, for high exposures. And but I guess for detection, characterization, what is important is also the contrast. So I was curious, what kind of exoplanets can we, I mean, what masses can we go up to with MARVEL?
Yeah. So here, for example, I did not specify, but sub-Neptunes I chose based on masses between 4 times Earth's mass and 20 times Earth's mass. So this is kind of, I set kind of a category for sub-Neptunes. So this is, so if you really go to 1 meters per second, you can go down to few Earth masses. Especially in very close orbital period where you see the white space, this will be filled by rocky planets. So there could be a couple of Earth mass planets. So that would be really interesting.
Thank you.
Still have time for questions.
I first want to try answering your question, Andrew. I think the name of 4 telescopes are MARVEL 1, MARVEL 2, MARVEL 3, MARVEL 4. I don't think that's the right answer, but anyway, thanks for the great talk, Kaustubh. I have a very naive question. So when you look at the, when you take the transient, the spectra of these planets, how deep can you go in the atmosphere? Like how much information can you gather, like going inwards?
Yeah.
And can it help put constraint on the 4 scenarios that you showed? Like, has it like, if we take like more observations, in any way, like have these observations been helpful in disangling like which of the theory is like closer to reality?
Yeah, so I do not have a figure for that, but in general, like if you look at spectra from, for example, JWST, generally every wavelength bin probes a different pressure depth in the atmosphere. So these pressure depths could be in between 10 bars, which is quite deep in the atmosphere for some cases, to less than 1 millibar or 0.1 millibar even. So it is a wavelength dependent thing. So for example, some of the lines you can say, okay, this really probably is coming from the pressure region of 1 bar or 0.1 bar. So you can make these determinations based on the transit depth and the spectral line. So this you can make. And I think your second question was, what does this tell you about rest of the planet, right?
Well, does it help solve the, like, so in one of the slides you showed like 4 different theories of the composition of sub-Neptune planets. So can it help that picture in any way? Yeah,
so there are a lot of moving parts to these models. I'm not working on the upper atmospheric chemistry, but here, for example, Linus and Thomas, they are working on this, and what they try to also include effects which take you away from chemical equilibrium. So whatever I showed you was under the assumption of chemical equilibrium. But if you go above so until, let's say, 100 bars or something like this, chemical equilibrium is a good proxy for what's happening there. But these are optically thick regions you cannot really see. But as you go to the optically thinner atmosphere, in these regions, a lot of disequilibrium effects take place, like transport quenching, photochemistry, and all these have been very well modeled in the community. And a lot of people are working on this. So I think the idea for me in the future is to couple what I know with these different effects. So this will then allow us potentially to say what it means for the deeper layer structure and composition. So it can probably, we can make a choice out of the few I showed.
Thank you.
Okay, thank you for the very nice talk. There seems to be a discrepancy between what instrumentation folks understand under 1 meter per second and what the exoplanet scientists understand. Okay. So what we understand is the individual measurements are 1 meter per second, while in your slides I always see that the semi-high amplitude should have a precision. Now you can reach that semi-amplitude precision of 1 meter per second even if your individual measurements are 2, simply by taking enough measurements. So is it the semi-amplitude that you need to know very? Yeah, so this is also, I think this came up at the last consortium meeting, and yes, indeed, if you look at this equation I showed, a lot of, so I can double check this, but what I understand is K is generally the semi-amplitude. So what you're saying is right, and I think we need to homogenize this in our discussions, what really we mean. So yeah, okay. I agree, because yeah, for you it's like from one peak to another peak, right? So yeah.
Maybe to follow up, Kaustubh, if you could go back to the plot you've been showing answering Shreya's question, where you have this RV thresholds of 5 meters per second and 1 meter per second. So what are those? So what do you mean by RV there? Is this K?
Yeah, this is semi-amplitude.
Okay.
So at least the way I plotted it, it's semi-amplitude. That's so why I clarify there. If we say that the goal of MARVEL is really a full amplitude of 1 meter per second, then this plot needs to be corrected.
But so it's not the RV precision that you need per se. You need to be able, to be able to detect K value of 1 meter per second. Is that correct?
Yeah.
Okay.
Yeah.
Hi, Kaustubh. Thanks for the talk. Can you go back to, I think it starts from slide 31, where you had all these beautiful predictive plots from theory? Yes. Mm-hmm. So since it's still in prep, here's a tip. Could you make it clear to your readers by giving some error bars in these plots of what different instruments can deliver you, and if it will at all be able to allow you to discriminate between all these beautiful models?
Yeah, so the thing is, this is something, I agree. So this we are trying to do for another plot, which is more connected to observables. So here we are really probing the surface pressure. And there is no way to determine this at all with any instrument. But this is also a very important point. So thanks for bringing this up. Should be able to connect to some instrumental facilities, which will make it really put it into perspective. What does this mean in terms of what can we observe?
Thanks, Kaustubh. It was a marvelous talk indeed. My question is slightly tangential, but I guess what I want to know is there room in the completeness of like the physical completeness, not the inclination angle completeness? So when you take that out, is there room in the remaining completeness of, say, transits or radial velocity measurements for our solar system to be normal? So we know there's a parameter space we can reach. How much of the remaining parameter space, right, when you take out the inclination effects, remains, say, like if you had a volume limited sample, I take all the stars, I take out the inclination effects, just to say within 2% or something for transits, and then I say, okay, and then I see this many, whereas I expect to see this many that might have an orbital plane that would be observable. So like, do you have a feel for what that rough number would be to within like 10%, and then?
So to understand your question better, so you mean because we are probably biased currently to transiting planet populations, what does it mean for non-transiting planet populations or no?
No, not quite. I mean, if you assume that there's just a random distribution of inclination angles, then what I'm saying is there will be completeness due to that, but that can be taken out just by assuming something like that. But then what remains would be your physical completeness. For example, if we just think about the masses of the planets and not the separations, like for sure you're more biased towards the more massive planets. What my question is, what fraction, when you take out the inclination effects of planets, is calculated that we are observing? So if the inclination effects are on, like what is the completeness of, say, the transit method at the moment? Like is it then reaching something like 10% of the expected, are we finding planets on something like 10% of the expected systems with inclination angles where it would be viable anyway? Or is the number higher or lower? Because then I imagine just on that argument alone, you could already start to answer some questions on whether something like our solar system even could be typical. Because if the completeness is very high, then there's no room for it to be typical.
No, so as far as I understand, so this is a matter of people doing population studies. As far as I understand, I think it's fairly understood by now because beyond Kepler, there have been quite a few homogeneous surveys. Kepler is one of the best, but there have been quite a few. And this all points to the same story, that giant planets are much fewer than small planets. And a lot of small planets, at least for the planetary systems we are looking at currently, they are in resonant chains, quite a few, more than people thought there would be. So all this points to that our solar system is a bit unique. So earlier understanding 10, 15 years ago, I read was of the order of 10% already, and now people say of the order of few percent. So yeah.
Okay, That's super interesting. Thanks.
Yeah, last one.
So I have one more question. So in these two plots, in one of them, the composition of hydrogen is like quite high. So it is hydrogen dominated, but the other one, it's relatively low. Can you a little bit describe, like, I mean, it's kind of a stupid question in some way. I mean, it is hydrogen dominated, but how you go
so
from that to the magma dominated picture?
So you mean how we go from like this orange line making most of the black
Yes.
to the orange line being here?
Yes.
Yeah, so actually hydrogen has two major forms, H2O and H2. And H2O is water vapor or steam, it's very soluble in magma. So you lose most of this hydrogen through the dissolution of H2O. But also, H2 also dissolves. So there are chemical reactions going on which also change how much H2 versus H2O is present. But then, nevertheless, what we see is, so for example, the blue line is H2O. It also drops by almost the same factor. So this is because the whole, all hydrogen-bearing gases get dissolved to certain amount, and this changes the resulting chemistry. So that's the first order effect. There are few other effects due to real gas behavior, reactions between some gases which happen differently on the right, because now you are not in a hydrogen-dominated system, but hydrogen-poor system. So this also changes the composition.
All right, I'm afraid we have to stop here. Let's thank our speaker again. In case someone cares, the 4 telescopes of MARVEL are still unnamed. Propose the names. Thank you guys, see you next week.